All right, hi everybody. It is AER 110 DE slash WX. A lot of letters there, and we are on lecture number 3 of this portion of the weather part of AER 110. And we'll just get right into it right now. Hope that you had a nice weekend. We're at the mid term point in this particular term, the March term. Okay, let's see. I guess everybody is with us now. I assume people can hear me. It's Mitchell and Barbara and anybody else who wants to join. We are recording, we are sharing, and we are moving boldly forward now. Okay, let's take a look at our weather. The weather has been pretty nice across interior portions of California. You can very clearly see the very conspicuous marine layer, which doesn't generally get going big time until May and June. That's why they call it May gray and June gloom. But here it is still April. What is today? The 22nd. And it's pretty warm in the interior portions of the state. Let's take a look at some of the temperatures now. Right now, it is 83 degrees in Bakersfield. You can look at it here. We're going to be talking about synoptic weather later on today, so we'll just sort of dive right in. Here in thermal, it's up to 89 degrees. Do we have any 90s? Even up here at China Lake, it is currently 89 degrees, pretty close to 90. And so whenever there's a lot of heat in the interior, here's Las Vegas at 89 degrees. And of course, in Needles, it's 96 right now, so pretty hot over there. Anyway, whenever there's heat in the interior, quite often due to upwelling in the cool water of the Pacific, you'll find temperatures kind of cool. All right, let's see who needs to. Okay, let's see here. Who is not muted? Ah, there. Okay. It says you're unverified, Barb. I don't know why that would be. I certainly verify you. So.
Okay.
Okay. All right. So let's see. We have more people on board now. Good. Okay. Back to what we were talking about. So the low clouds and fog develop with the marine layer, and you can see temperatures are in the 50s and 60s along the Southern California coast. Got some drizzle here in, let's see, right here in San Clemente. Yeah, all right, light drizzle and a little bit of light fog, 700 overcast. So yeah, it's pretty. Let's take a look at a sounding. We're going to go ahead and take a look at a vertical sounding from first Bakersfield. Here's Bakersfield. This is like right now. And you can look and see the temperature as we go vertically here. Here's 5,000, 10,000, 20,000 feet. So the temperature slowly goes down and the dew points are over here pretty dry. That's Bakersfield. But if we were to take a look at, say, Oxnard, let's go to OXR and see what it shows. The sounding here is pretty dramatically different. You can see that there is very cold air here. Temperatures are in the 50s Fahrenheit. The temperature and dew point are the same. And then we have this inversion where the temperature goes up with height rather than down. And that's how you can tell this is the marine layer right down here. I could pick any other location along the coast and you would see a similar marine layer. Now, the question is what will happen in the later today. So let's go all the way to like 23Z, which is right here. That would be 4 p.m. See if it breaks up. Well, a little. You can see there's a little bit of daylight between the temperature and dew point there, but for the most part, still a pretty significant inversion. And let's go out like tomorrow at the same time, 23Z, and see if it's any better. No, looks like there's going to be a marine layer there too. So the
Miles,
marine layer is here. Yes, go ahead, Mark.
can you go back to yesterday?
Yes, I can go back to yesterday. You mean in the soundings? Let's go. Let's
Yeah.
do that. All right, so let's go back to the
try
20.
9 a.m. and then more like 3 p.m.
9 a.m. yesterday, which would be 16Z on the 21st. Oh, it doesn't have it. I guess it doesn't go back quite that far. Let me try 3 p.m. and just see if that works. You know, there's a limit. Sometimes it doesn't go too far back, but we'll go to 22Z and see if that works. There it is. Okay, well, we got that. So there's 22Z, 3 p.m. yesterday in Oxnard, California, and you can see a pretty significant, looks like an inversion there, and it clears out quite quickly off above it. Were you flying yesterday?
I was flying yesterday afternoon. It was low IFAR most of the morning, like 300 feet. Now,
Okay.
can you look at the same time for Fillmore?
Possibly. Let me go back to KOXR and see what the weather was like. We'll go back to the last 48 hours and just see. Okay. Sounds like you're eating lunch.
I am eating lunch.
Okay. So let's see. This is yesterday right here. Oh, yeah. 300 overcast, 2.5 in fog, 300 overcast. Did it ever break out? Wow, it never broke out. Ever, never.
Nope.
But I'm sure if you took off, it was like clear right above it, right?
The top was 12 to 1,300 feet.
Really?
And it cleared out quite well at Camarillo. That might be the other one to look at, is Camarillo.
Okay, let's look at
what the sounding looked like there.
Well, let's look at Camarillo's data first. Okay. All right, so yesterday, we'll go yesterday morning. Okay, so nothing. Wow, nothing at all in Camarillo. That's CMR, right?
KCMA.
Oh, no wonder. Duh. You know, I knew that. Okay, I was crazily, okay. Now this is more like it. Okay, yeah, CMA. What was I thinking? What is CMR? Let's see, where is that? I don't know. I'll have to figure it out. All right, so Camarillo. Let's see here, 300 overcast, and it did clear out right here. Right there at 2036 Zulu, went to 1200 few, and then clear after that. But then, boy, it came right back right there at 106. And let's see here. And Fillmore, you wanted Fillmore? Let's look at Fillmore. Oh wait, let's look at Camarillo. That's CMA, by the way, CMA. Okay, CMA. Okay, this would be yesterday at 21Z. And what is going on here? I don't want this. I don't want this. Why is it doing that? Okay, let's not do that. Let's let's look at Camarillo and see what's happening in Camarillo and see what you had there yesterday. So here's the dew point, and we'll go to Camarillo. Fillmore, I'm sorry, Fillmore. Let's go to Fillmore. So Fillmore it is. Okay, Ventura, here we go, right about here. Okay. So it looks like at your house or nearby yesterday. Here it is. Okay, we'll go to 21st at in the morning. Looks like temperature 66 dew point 50. It doesn't actually have, I'm sure, 47% humidity, so it was nice weather there. And this morning, looks like you got some low clouds this morning, huh?
We still have them.
Oh, yeah, temperature 58, dew point 56. So you're like socked in. Of course, I knew that by looking at this. So let's just come right down here and look. Oh yeah, you're in the, well, I don't know. It looks like it's beginning to maybe clear out. What's it look like right now?
Gray. I can't see the hills behind me. So it's probably 300 or 400 feet.
Yeah, but it's going to definitely improve. I can guarantee you that. Hey, while we're at it, let's take a look at these neat little eddies. Here you can see some Channel Island eddies right here, this little low pressure system, which really isn't a low pressure system. It's just a little circulation. And this is the Catalina eddy right here, where we have winds coming down the west coast, and then it comes around the lip of Point Conception here and causes this little left turn to the clouds, and they have this neat little pattern right here. It's always fun to look at, and you'll always see stuff like this in very stable air masses. Farther down to the south in the San Diego area, all the way into Baja, you can see that the clouds come right up into the mountains there. Here we have the Inland Empire. It looks like we had some clouds this morning, but the thing is completely clearing off now. And if you look very closely, you can see some high, thin clouds that are streaming over the top. We'll come back to a wider look here. In fact, we'll come back to a really wide look right here. And it looks as though the low clouds are like creeping their way up the coast. They're up north of the Bay Area now. And there's a low pressure system over here too, way off the coast. Let's see what it looks like in the mid-level water vapor. Okay, yeah, you can see a lot of contrails. Look at all the contrails here. Those are all contrails made by jets in kind of a high, cold, humid atmosphere. All right, back to our weather. Let's see what's going to happen here. Here is the West Coast, and you can see here. And zoom in. There we go. We're going to zoom in. All right, so it shows a lot of dry air. This is a water vapor imagery. It shows a lot of dry air, but I couldn't help but notice a pretty strong west to east flow way south of even Hawaii. Here's Hawaii, ostensibly in the tropics, but we have very strong westerly flow there. In the tropics, generally you get easterly flow. You get trade winds and things like that. Here, this is a very notable difference to that. So we'll see if that has any significant impact. All right, we're going to look at weather once again. Let's go to this, and we'll come back and just look at our conditions here. KBFL, KOX, OX, OXR, KSAN, and KPHX. And we don't need to go back 48 hours. That's too many. We'll go back 3 hours and look at the TAF and see what we got. We will check it out here. Okay, temperature in Bakersfield is now up to 28 degrees Celsius. This is going to probably be one of the warmer days of the year so far. It was 2 weeks ago, Friday, that we hit 91 degrees. Today we'll be up there close to 90, maybe upper 80s. And otherwise in Bakersfield, just not too much going on, just a few to scattered high clouds. Winds, as you would expect, typically out of the northwest to 9 or 12 knots during the afternoon. Then it clears out and drops off at night. Oxnard continues to see overcast at around 700, 5 miles visibility, light fog. The only difference here is that we're going to begin to squeeze out some drizzle right there at 8Z tonight, right around midnight. Look for 800-foot ceiling and a little bit of light drizzle. And the reason that would happen, by the way, is due to a little bit of vertical motion in the marine layer. That's what causes drizzle. That's what we had earlier. I think I showed an observation with San Clemente Island, a little bit of light drizzle. San Diego, on the other hand, we've got 1200 overcast. Temperatures are cool, very much like May or June. But again, this is a lot. Much of this is due to the very warm air mass that we have, which is only going to be today and tomorrow. After that, things are going to completely change. So 1,000-foot broken. And then it goes up to 1,500 feet by 19Z, which is like now. And then temporarily for about 4 hours right here between 20 and 24Z scattered. So VFR, but then it's right back into the, I don't want to say soup. It's not going to be that bad. Marginal VFR at 2Z tonight. Phoenix, no problems there. Wait a minute. Maybe there is a problem. What is this right here? Okay, runway visual range on runway 07 left is down to 2,400 feet. All right, so that's not due to anything probably weather related. I don't know what would cause that. Generally, if you see runway visual range like you see right here, that means that the visibility is really low because something's happening. It could be blowing dust or fog or rain or something like that, and none of that is happening. However, sometimes a plane can go by and kick up some dust as it's turning, or maybe there's some smoke in the area, something like that, and very temporarily there'll be a lower RVR. That's what that is. It's nothing to worry about. And of course, there's nothing in the forecast that says anything at all about obstructions to vision. So skies are either clear or few at 25,000 feet with low winds, light winds, and good visibility. So no problems there. We'll take a quick look now at the forecast. So here is the forecast for Bakersfield, and we're looking at sky conditions here, and it's just nothing but almost clear skies. Here is the time up here is 18Z, 21Z, 00Z. So this would be 5 o'clock this afternoon. Temperatures get up to around 88 degrees, but tomorrow's high only 81, and the next day only 76. So definitely cooler weather coming shortly. We'll go back and perhaps we can take a look at a few others here. There's KOXR, KSAN, and KPHX. And we'll take a look at the extended to see what's going on into the future. And what do we have here? It looks like there are some clouds that are going to come around along about Thursday and Friday, but temperatures noticeably cooler, 70s for highs, low 70s of that by Friday. Chance for precipitation pretty much negligible. In the Oxnard area, we've got the low clouds, 88% of the sky covered with clouds. But then, as you can see, for the rest of the week, beginning really Wednesday, just clear skies. And temperatures will be, let's see, what are the temperatures here? The highs and lows right here, 50s for lows, 60s for highs, but not much in the way of any significant cloud cover. Phoenix will be close to 100 degrees. Here's 97 for tomorrow, and then a little cooler after that. And in the San Diego area, what do we have for sky coverage? Well, it looks like we do keep some clouds there. So now I want to know what is going on. So we're going to take a look now at that. So let's go to pivot. We're going to pivot here. We're going to look into the future and see what it's. First, the big picture here. Here's the big picture. We're looking at California down here. It looks like there's low pressure way off the Carolinas there. And as we go into the future now, it looks as though there's a little weather system that wants to come by. Maybe some, wow, it even shows snow up in the High Sierra here on Wednesday and Thursday. I wouldn't be too concerned about that. But here comes the next system and a little bit of light precipitation, really not too much. This is the most dramatic one right here. This is a week from Tuesday and Wednesday. So a little over a week from now, it shows a very strong low pressure system pushing on through. Let's just take a look at it in the upper air. So we're going to go to the 500 millibar anomaly and see what it shows. In fact, we're going to go ahead and take the big view here, the continental view, and here it is. Okay, ready and go. All right, so here we are. Here comes low pressure right here, right there. Over Southern California, that'll be on Wednesday and Thursday. A little bit cooler, and then another little low dives down right here. There it is. And this is the one that gives us just a slight chance for a little bit of light precipitation, but I don't think anything's going to happen. After that, it moves on out. Now what? Okay, now the models have suggested, and it looks like they're doing it here, like another big low pressure system. So the time is in the upper left-hand corner. That is May 1st at 3Z is what that is. And it shows very decidedly a much cooler weather going into the month of May. And then here's another low. What's this? It looks like it's coming down and giving us a good chance for precipitation, perhaps on May 5th, Cinco de Mayo. Okay, and after that, things look a little bit better. Now I have to look at the European model as a balance to all that and see what it says. Okay, first, it keeps low pressure out to the west of us. It takes that low just to the south of Southern California, maybe into the San Diego area on Thursday. And then that second part comes by, but it really is an inside slider. It stays well to the east of California. And then let's see what happens with the next system. Looks like it's beginning to develop. Another problem with the European models, it only goes out 240 hours. So here's 240 hours. It takes us through 12Z a week from Thursday. The American model that you looked at earlier goes out 384 hours. And so that's just simply farther into the future. And that's kind of cool. But this also shows a big high pressure system over the east, and that's going to probably cause very hot temperatures there, which will cause probably a reciprocal cooling here in the western United States. We'll look at one more thing here. Here's the CVS, the CFS, not the CVS, it's not a drugstore. And this is the climate forecast system, which goes way out into the future, goes out 750 some odd hours. So there's that same story. You can see the low going just to the south of us. Here's the second part, which completely misses us to the east. And then we have the low there, and then another low. Doesn't really show much. going into the 5th of May. That's Cinco de Mayo. But then we have, in fact, it's not showing much at all. So this is, well, wait a minute, here comes something. There's low pressure, which develops very dramatically right around the 16th, 15th, 16th of May. So the middle of May, there will be, if this verifies, a chance for rain, I think. And then it keeps it kind of cool. And that goes all the way through May 24th. And that's as far as this goes, which is way out into the future. And one thing to remember is that the farther into the future you go in a computer model, the less accurate it is. I can look at one other thing here. We can look at the surface and precipitation just to see if it wants to bring any significant precipitation. Can I get any closer? I guess I can. I will do this one here. We'll take a look at the national. Okay, and so this is that same climate forecast system. It shows, now just look at the western United States here, and it shows a very strong pressure gradient, and that would be right there. And this is cooler on a Thursday and Friday. Friday is going to be the coolest day, probably 70s for highs in the Bakersfield area. And we'll probably get rid of all of that marine layer. Cloudiness.
I have a question.
Yes, go right ahead. Love
Okay,
questions. Glad you're asking. What do we have?
So you stated that the farther that we, go into the weather, that
Yep.
we could that the less accurate it becomes. But how much inaccurate would it become the further you go?
Is this Ivan?
Yes.
Hi, Ivan. Okay, so well, the rule of thumb is that computer forecast error doubles every 5 days. So you'll look into the future, and of course the future forecast is based upon your analysis now. How correct are you with your current analysis? Because you might be wrong. It might say there's a low pressure system with a certain intensity, and you're wrong about that. Maybe it's more intense. Maybe it's less intense. Whatever your error is now will be magnified into the future. So you get 5 days into the future. So today is what? Monday. So Tuesday, Wednesday, Thursday, Friday, Saturday. By Saturday, there's a certain error that's baked in. So the rule is that you go another 5 days to the 10th day, and then whatever that error is, it will be doubled. And then you go to 15 days into the future, and then whatever that error is will be doubled yet again. So that's kind of the rule of thumb. Now, forecast models are getting better. They're a lot better now than they were, say, 20 years ago, or even 10 years ago. And that's because of breakthroughs in technology and all that. But we will never, ever, ever, no matter what happens, be able to make a perfectly accurate forecast of, say, 2 weeks from now. And we won't be able to say, in fact, let's take a look at it here. So we'll go to the future. We're going to go this right here. And here is a future forecast. And this forecast is for Bakersfield up here. You can see it's Bakersfield right there. And this is the high temperature forecast for 251 hours from now. It says 81 degrees will be the high temperature on Thursday, May 2nd. Well, the chance of that actually happening is actually pretty low. Being within, say, 2 degrees. Now, being within 10 degrees, maybe, so as you go farther into the future, you have to just widen and widen your window of verification. But there will never be a time that you can say, today is whatever day it is, and 2 weeks from today, the temperature at 3 o'clock in the afternoon will be this exactly. That will never happen any more than you'll be able to beam somebody up. That too is something that will never happen.
But you said that you said that the error is like doubled. So
right.
Well, so how would that work? Like that's 2 weeks, right? So maybe within like a 10-degree error is what we should be expecting, right? Not a double, but by the next 2 weeks, what do we expect, a 20-degree difference? Or
yeah, and after a while, if you start talking 20-degree difference, then you don't have any skill. And skill means that your forecast is better than just climatology. So climatology is just the average temperature, the average chance for precipitation, the average wind based on, 30 years of data. So you can come up with this data set, which is just whatever the average is. If you can do better than what the average is, that's called skill. And of course, weather forecasters, that's what it's all about. I mean, without skill, what are you good for? Nothing. So, for example, the forecast for, let's see here, for San Diego, for just coming up in a couple of days here, let's say here's the San Diego forecast for Wednesday. Today, that's 2 days from now. So the San Diego high temperature should be 67 degrees. Well, the climatology might say something like 72 degrees. So if it's actually 67 degrees, that would be skill. That means that we know something that we wouldn't otherwise know because of all the technology and stuff like that. So computer models, and we'll take another look at a computer model here. Oh, here it is. Okay. So here's a computer model. It tells us what the weather should be like, but as we go into the future now, and you can see the forecast hour right up here. 492. That means 492 hours from the initialization. So here it shows that there will be rain over Central California on Saturday, the 18th of May. That's the 624-hour forecast. Is there skill? Well, if it rains, there certainly is skill, because I think climatology would say it probably isn't going to be raining that time of the year. But anyway, that's just sort of a glimpse into the world of computer forecasting and accuracy and what exactly we're trying to do. It's all numerical weather forecast. And by the way, let's see, is it the next one or is it the one after? I think it's the one after. It is 1 week from today, we're going to have a class on Introduction to Numerical Weather Prediction, which is models. And it turns out that people have been forecasting the weather for a long time. Farmers have been forecasting, ranchers have been forecasting the weather for thousands of years, actually. And why? Because they have to be able to grow crops and to survive. But they haven't used numbers. They've looked at the sky, they've looked at woolly worms, they've looked at horse manes and things like that, just to get some insight into whether or not the weather is going to go one way or the other. But in the 20th century, numerical weather prediction came into being because of the ability to understand the atmospheric equations and the science of it all. And so that's where we're at now. We're just trying to get better and better. But I'll say it one more time, we will never get to the point where there is a perfect forecast. In the movie Back to the Future, let's see, I think it was the second one, when they went way into the future to the year 2015. I don't know if you saw that or not. The rain started at exactly 2:25 or something like that, and Dr. Brown said, yes, the National Weather Service is really good now. That will never ever happen because there's simply too much uncertainty. There's too much uncertainty in the vast complexity of what we call the world. All right, I have kind of gone on and on there. I kind of apologize for going on and on.
I have another 2 questions, if you don't mind.
All right, question number 1.
All right, I might have missed it, but where does it get its predictions from? Is it just based off of previous weather on that year? I think you stated that, but is that where it's getting its predictions from?
Where what
history?
is getting its prediction from? Where the computer
The
model?
national, yes, where is, like you're saying that this is getting its it's predicting the forecast, right? But where is it getting the information to predict? Is it just based off of previous history?
Well, it's looking at the current situation. It's looking at the current satellite. It's looking at the current observations. It knows what the 500 millibar and the 300 millibar. Here's a 200 millibar winds right here. It has a pretty good idea of what's happening now, 3-dimensionally. It knows what the temperature and the winds and the humidity and momentum and vorticity, and it knows all of these parameters. and then based on equations of what the atmosphere should be doing based on the ideal gas laws and things like that, it can predict in time steps into the future, like minute by minute by minute, what the weather should be like all the way out to 16 and a half days. But
Right.
it just simply, it knows what the weather's like now because it can, here it can take a look at weather observations. It knows what's happening. Let's, where is it here? So here is your weather observations. All right. So it knows that it's 90 degrees in Las Vegas. It knows that it's 71 in Flagstaff. In fact, not only that, it knows what the weather's like in Siberia. So here it is at Petropavlovsk, it's 27 degrees right now. And all the way down at the South Pole, it's like 60 below zero. So it knows what's happening. It knows all that, and it can input that data into a computer model that will then solve all of the sophisticated differential equations to come up with a forecast. All right, what was your second question?
Second question, this might be off topic or unrelated. Because you said that there will never be an exact number and you can never really predict it, right? Do you like foresee like that becoming like, like there's sports gambling? Do you think there'll be weather gambling?
Will there be weather gambling? Hey, why not? Actually, there are ways to do that. There is, who does it? The University of Oklahoma. I wish I had their weather site right now, but they have a thing where that you can predict what the weather's going to be like in these places, like Grand Forks, North Dakota, and Boise, Idaho, and a few other places, and then you will be verified on that. And if you are the closest, and this is called weather competition, and there are people from many different colleges all across the country that we used to do that here at the CAU too, and you would be part of a group, and then your team would guess what the high and low temperature, winds, precipitation, all that stuff at all these different locations. And then if you were the best, you got a trophy. So, but I think what you're getting at is this. So we are now doing a thing where we make the forecast based on probability. Everything is probability. Let's see if it says here. Let's see. Okay. So do we have any probabilities here? I'm looking for probabilities. Earliest date, cooling trend, projected precipitation. Everything is probability. So if I were to go to, let's do this. So here's probability. So we're looking at probabilities now. So here's Bakersfield. And these are, this is sort of getting into the weeds here, but this is the probability from this particular run that the temperature, the TX, which you see the first two things there, the probability that we will be in the 90th percentile, the 75th percentile, right? This is the 50th percentile. That's what the 5 means right there. And it gives you a range of temperature so that you know what the probability is that you will be above or below something. And so everything is probability. So there are two different ways of looking at a forecast. It can either be deterministic, which means it will or it won't. It will rain or it won't rain. There's no shades of gray. Or there is a 20% chance, 2 chances out of 10 that there'll be measurable rain, or there's 80% probability. And everything today is probability. So here we have probability of wind speeds, we have probability of gusts, we have probability of pressure. Let's see, probability of ice. Yeah, here's the sea level pressure probabilities. So, and I won't go into the details on how you actually interpret this, but let's see if there's another place that has probabilities. Maybe down here in Los Angeles. Sometimes the National Weather Service, they make these graphs based on just probability of this, probability of that. Let's see, and we don't have any. There's just not that much going on, apparently. We'll try one more time. No, it doesn't really show it there. But anyway, everything is based on probability. So Ivan, it's all about what are the chances? Are the chances good? Are the chances bad? But I'll tell you this, the chance will never be 100% or 0%. Well, unless it's raining right now. Okay, if it's raining right now, then yes, the chance is 100% that it will rain.
Right.
But otherwise, everything is just shades of gray. Did that help?
Yes, but something that's like a bit conflicting is that you say like it doubles every like week, but I feel like it's more. I feel like it's more of a curve thing because I feel like there's a certain point where there's a certain range based off of history and like you said probability that it won't ever like I know you said that there's 0% chance, but there's like it's expected to be within that range and at least it's close to like 0.0001% chance. Yeah, there could be a huge hurricane, but like the chances of that are like basically close to zero. And
Right,
so I
right.
feel like
That,
it
that's
doesn't double.
That's true. The chances can be very close to zero. It's sort of like an asymptote. You approach, the limit of something, but you never quite get there. It's like there is a chance that I will die within the next minute, but there's a very low, low chance of that, but not a zero chance, something like that. There's a chance that, an asteroid might hit, all these things. And in talking about the curve that you were referring to, I said, model data error doubles every 5 days. You do get to a curve where you just simply blend in with climatology. So whatever the climate says, for example, let's go to this, and we're going to go to this, and climate, we're going to go here, and we're going to just take, okay, we'll take Bakersfield, and we're going to just take today. So here's here's April. So here are the days on the left, and here's the maximum, minimum, and average normal temperature. What is the 22nd? So here's the 22nd right here. Okay, so if you look at the 22nd right here, or I tell you what, let's go a week into the future to the 29th. All right, so the normal high is 80 on the 29th. So if you are looking at a forecast, it will then, the window will widen for verification, but it will just basically trend and curve toward whatever climatology is. So climatology is 80 for a high, 54 for a low, and 1/100 of an inch of precipitation on that particular day. And that's climatology. If you want to look at like July, we'll go to July. Hey, you're making a forecast for the 4th of July. So the 4th of July, the normal high in Bakersfield is 97, the normal low is 70. And you could make a forecast based on computer models and sophisticated equations, but or you could just simply trend toward the climatology, and that is the ultimate. By the way, it never actually hits 100 degrees for a normal high; it just gets up to 99. just for fun there. All right. Are there any other questions, Ivan, that you have, or anybody else? It's good to have so many people on board here. Barb, you got a question?
Actually, no.
Has it
So I
cleared
will
out?
make the comment that I think Penn State did the study that anything past 10 days is very suspect.
Oh,
on
absolutely.
testing.
Yeah. Right. And what you do is anything past, 10 days or 2 weeks, you just simply blend into whatever climatology says, because that'll always be there. Okay. Let us then get right into today's topic, because it's actually a very big topic here, and I hope we haven't gone a little bit too overboard here, because there are a lot of things I want to talk about. Synoptic weather. Right, here is that synoptic weather map. It takes all of the weather observations from all the METAR observations, and you can then come up with a sort of the headlines. And whenever you see fronts and highs and lows, we're just basically talking about the headlines, not the details. If you want the details, you can go right down to the METAR observation and see what's happening. But the highs and lows, those are the headlines. And that's what synoptic. It means a synopsis, sort of the overall broad picture, not the details. So wind is made from uneven heating of the atmospheres, uneven heating of the earth, which causes high and low pressure systems to develop wherever there is warmer than normal, unstable, less dense air. It will rise, and then all of a sudden there's no pressure there. The air just rose, there's low pressure, and so then that is then filled in from high pressure systems someplace else because of the differential heating of the land and the water. All right, let's take a look at this. If we haven't already, this is pretty important. This is the general circulation of the atmosphere. So here is 0 degrees latitude. That's the equator. And a lot of heat comes down, a lot of solar radiation, a lot of shortwave radiation. It gets hot. It gets hot near the equator. Now, the most direct rays of the sun, they do go north in the summer and south in the winter, as you know, between the tropics of Cancer and Capricorn. But most of the time, pretty direct rays right around the equator or close to it. So all of this warm air rises and it goes higher and higher and gets up to what's known as the tropical tropopause. That's up around 60,000 feet. But then once it gets there, as you know, in the stratosphere, the air is warmer and that is more stable. And so the clouds and the updrafts cannot just go on to the moon. They come to an end. They stop. They hit the ceiling. And so then they have to move to the north and to the south, away along the tropical tropopause. And what they do, we'll just go ahead and take the northern hemisphere here because the southern hemisphere is just a mirror image. So the air continues off and then it begins to sink right around 30 degrees north. That is a high pressure system there because we have all of this air which is sinking and making a mountain of air mass right there. And so we have sinking air at 30 degrees. So you might wonder, why is it at 30 degrees? Why not at 20 degrees or 40 degrees? That's a good question. I think it has to do with the specific size of the world. If the world was the size of Jupiter, then there might be more cells, but there's only 3. And because of, and it's nice round numbers here too. So 30 degrees north is where, as it turns out, all of the air, which is traveling north from the equator, actually sinks and settles. And then once it gets down here, it then will return to the south toward the equator, or it'll go to the north because it can't go into the ground, obviously. So there's a limit here. So this is called the Hadley cell, and it was discovered by a guy named Hadley way back in the 1600s and 1700s. And this was the individual who basically defined and not invented or discovered the trade winds. So we have winds that blow from the northeast in this area here in the tropics. That's called the Hadley cell. So this goes round and round and round again. Now, what about up here? Okay, so now we're up into another part of the world, and so now winds are going from high pressure to what is going to be low pressure right there at 60 degrees north. So you might wonder, well, what happens at 60 degrees north that is so important here? Well, this is just part of this is a cog in a machine. All 3 of these cells are cogs in a machine that are all the same size. So the Hadley cell is where it all begins. It all begins with hot air at the equator, and then the air sinks here to 30 degrees. Then it begins to move north and south until it gets to a point where it begins to rise again around this, what is known as the Ferrel cell, named for a guy named Ferrel in the 1800s who discovered this. And so now we have upward motion here at 60 degrees north, and the air rises up to the mid-latitude tropopause, which is more like maybe 40,000 feet. It's a little bit lower because the atmosphere is a little bit cooler in general. And so we've got this taking place. So this is a very important point. We have low pressure systems right around 60 degrees north. There are semi-permanent lows, the Aleutian low, the Icelandic low. But why do we have low pressure systems there? It's not because it's so hot. It's not because it's so hot. That all is down here at the equator. That's where it's hot. And that is where this whole procession of cogs in a machine begins. Okay, so we do have low pressure at 60 degrees north. And then, of course, we get up to the polar tropopause here, which is around 20,000 feet. And then finally, the air will once again sink at the North Pole. So we have a low, a high, a low, and a high at 0, 30, 60, and 90 degrees north. It just makes a lot of sense. It all fits together quite nicely. And here are those different cells down here. Now remember, we have high pressure right along the subtropical high at 30 degrees north. And because of the Coriolis effect, which we talked about last time, winds do not go directly from highs to low. They curve to the right, and that's why we have the northeasterly trade winds. North of the high pressure system, coming up to the 60-degree permanent, semi-permanent low pressure system, everything there also curves to the right, so we get westerlies. All right, boy, what a mess this is. I just have to clear this out just so it looks okay. That looks much better. Now you can see it. All right, so we have the Hadley cell, we have the Ferrel cell, and we have the polar cell. This is the general circulation, the Hadley, Ferrel, and polar cell, and all of this is then also mirrored in the southern hemisphere. We have west to east flow here. Within, I guess, the Ferrel cell, which is between 30 and 60 degrees north. And this is where we have low pressure systems and high pressure systems and fronts and things like that. Synoptic weather. Once again, here's high pressure at 30 degrees north. If you go just to the north of that, like 35 degrees north, kind of where we are in California, then you will find dry summers and wet winters. If you go just to the south of there, like to 25 degrees north, maybe down into Costa Rica or something, there you will have dry winters and wet summers. But right around the high pressure system, right around 30 degrees north, you will have, it'll be dry year round. You will have things like deserts, like the Sahara, like the Sonoran Desert, like the Chihuahuan Desert. In the southern hemisphere, you'll have a Kalahari. In southwest Africa, you'll have, of course, most of Australia, which is pretty dry. In the equatorial region, you'll have ample year-round precipitation. And in the subpolar region, which is basically the mid-latitudes, you will have precipitation year-round. And then you'll have very little precipitation at the poles. That is the general circulation. And of course, in the mid-latitudes, you will have high and low pressure systems. You'll have cold fronts, you'll have warm fronts, and then you'll have the mysterious occluded fronts as well. These are called synoptic features. There's a cold front. It actually has some 3 dimensions to it. It looks like a wedge moving down. It has about a 30-degree angle, 30 to maybe 40-degree angle from the ground up, because all of the cold air is sinking behind it. So it has that. Warm fronts, on the other hand, have a very shallow, maybe a 10-degree slope, because the warm air is just riding up over the top of the cold air. So here is, once again, a look at the weather map for a particular day. This would be in July. So looking at a weather map, we have a temperature, which is always in the upper left-hand corner. The dew point is always in the lower left-hand corner. Anything dealing with pressure is always in the upper right-hand corner. In this case, the 107 stands for 10, 10, 0.7. And so the last 3 digits to the nearest tenth of a millibar, that's what that is. And if there's any weather or any visibility, we'll put VV for that. If there's visibility, it is between the temperature and the dew point on the left side. And of course, there's a wind shaft and some barbs as well. So these are the different types of weather. So a cold front is a blue line with little saw teeth that show you the direction that the front is moving. It is the leading edge of a colder or denser air mass. That's number one. Number two is a warm front, and that is a red line that has little half moons or semicircles, and that show you the direction that the front is moving. It is the leading edge of a warmer or less dense air mass. And then front number three is the stationary front, which is just simply a boundary between generally cooler, denser air to the north or a warmer and less dense air to the south. Of course, it's reversed in the southern hemisphere. And then finally, we have the mysterious purple front here, the occluded front, which has the pips of both cold and warm fronts on the same side. And an occluded front is a very misunderstood concept. The occluded front is actually more about the low pressure system. So a low pressure system is here. Everybody says that, you know, when a cold front catches up with a warm front, that's when it occludes. Actually, an occlusion, which looks like this, there's the warm front, there's the cold front, there's the occluded front, is simply a expression of how deep the low pressure system is. What happens is that the warm air down here, the warm sector, is lifted up and over and around a loft. It is off the ground. All of the warm air is off the ground around a low pressure system. That is what an occlusion is. It's about the strength of the low pressure system more than it is about a front. It means that the low pressure system has become mature. It has reached its maximum intensity. It has occluded. The warm air has lifted up. It's off the ground entirely. That's how you know that it is an occluded front. And occluded fronts only happen in the mid latitudes, as we'll explain in just a moment here. A very important point. So when a front is beginning to develop, in other words, there are two different air masses and one's moving toward another, we have a thing called frontogenesis. Frontogenesis simply means a front is beginning to develop, and you can see how it is portrayed here. It's portrayed as a not as a solid line, but as a broken line with the little pips as you see them there. That means a front is beginning, which will then probably during the next analysis will be a solid front. You can have cold frontogenesis, you can have warm frontogenesis, you can have stationary frontogenesis, but you cannot have occluded frontogenesis. Very important point there. Notice that. Okay, on the other side, we have a thing called frontalysis. Frontalysis is when the distinction between two air masses begins to wash out, and looks like they're beginning to mix together, and there really is no boundary anymore. And so you can see how that is portrayed. It is a dashed line, but it is not, every dash does not have a pip. So it's like the cold front pip, and then not just a line, then cold front pip. You can have cold frontalysis, you can have warm frontalysis, you can have stationary frontalysis, and yes, you can have occluded frontalysis, because that means that the entire system is beginning to wash out. But you cannot have occluded frontogenesis, because an occlusion speaks more about the intensity of the low pressure system and what's happening with it than anything else. Any questions about that? Talking synoptic features here. Okay. So we'll go to this. right, next up, we have a high pressure system, which is simply the center of an area where pressure is lower in any direction from it. So it is the highest pressure in an area of high pressure. This is the high pressure center. Low pressure, and it is a blue H. Low pressure is a red L for low, and it is the center of an area of pressure that if you go away from it, it's higher in all areas. A trough is an elongated area of low pressure. There is an elongated area of low pressure, and then an elongated area of high pressure is called a ridge like that. Troughs and ridges. We also have a couple of other things. We have a dry line, which you can see right down here. A dry line looks like a little warm front, except it's not red, and it divides dry air on one side from moist air on the other. The temperature might be the same on both sides. So that's what a dry line is. And we find dry lines in Texas, Oklahoma, Kansas, places like that. Not so much in places like California. And then finally, a squall line at the bottom is simply dot, dot, dash, dot, dot, dash. Looks like Morse code. It's an instability line where a squall will take place. And a squall that is a character of wind. And so we have the winds like this, and then the winds will jump up like that. And this would be like 20 and 30 and 40 miles per hour. So if you have a gust, the gust will just be a little instantaneous increase. Pardon me. But a squall, when a thunderstorm moves through, maybe a cold front is coming through, you will have this extended period of strong winds. That's what the squall is. That's the definition of a squall. And so a squall line is simply that instability line, usually out ahead of a cold front where that takes place. All right, and so those are all a certain type of we have these tropical waves, tropical depressions, tropical storms, and hurricanes. Well, let me get into what that is exactly. Let me go ahead and do this, because there is a very important distinction, which many of you have probably never even heard of before. Sure, you've heard of tropical storms, but you didn't know that that was a type of atmosphere. So we have two types of general atmospheres. One is tropical, and the other is extratropical, which does not mean more tropical than the first. It just simply means not tropical. Okay, so and for each of those basic types of atmosphere, we have two different iterations, two different representations of them. So tropical simply means warm core. What does it mean? It means warm core. That means that the middle of this atmosphere is warmer than all around it. Sort of like a high pressure system is the middle of an area where the pressure is highest. Well, you could say the same thing just using temperature. So here we're looking at a high pressure system above a high pressure system. Now this little dashed line that you see here, this black dashed line, that is the dividing line between the upper atmosphere and the lower atmosphere. It's a thing called the level of non-divergence, which forget about that, okay? In fact, I'm sorry I even said it. It's right around 600 millibars, and it is simply the point at which there is separate weather systems above it and separate weather systems below it. And so that's going to be the dividing line. Think about 500 millibars and 300 millibars, which is getting up there 18,000 feet and 30,000 feet. We're going to call that upper atmosphere. And anything below that, 700 millibars and 850 millibars, that'd be 10,000 feet or 5,000 feet. That's lower atmosphere. Okay, so we have defined upper and lower. And that's all there is. There's upper and lower. There's not any middle or anything like that. Upper and lower. So in the upper atmosphere, we have a high pressure system. And you'll notice the little red line here, this is the isotherm. So it's warmer. Here's the 0 degrees isotherm. So it's warmer in the middle right there than it is on the edges. So that would be warm core. A type 1 tropical air mass is one that's a high pressure system aloft and a high pressure system down on the ground. If you were to look at the weather map on the ground, it would be a big high pressure system. This would be like the Bermuda High, which is a very typical kind of a tropical, it's a maritime tropical air mass. It's hot, it's humid, it's high pressure all the time. That is one iteration of a tropical air mass. The other is this one, number 2. And so that would be your typical tropical cyclone hurricane. This would be like the tropical cyclone that you name, like a tropical storm Katrina or something like that. It's a low pressure system on the ground. Of course, you know about that. You've seen the bands and you've seen the heavy, the eye and all of that. But aloft, it's a high pressure system, and it has to be. A lot of people don't know that. So if you see a hurricane, and you will see the counterclockwise cyclonic spin of the bands, the tropical rain bands, and they are. But if you look up at the high cirrus clouds, it's all a big high pressure system. Everything is going up like anticyclonically, clockwise. It's like a big high. And that's because the whole thing is warm core. All right, so we have 2 different types of tropical. Now, extratropical, this is the one that is like your mid latitudes. This is the one where we're talking cold fronts, occlusions, things like that. Everything that you saw just a moment ago in synoptic features. So the third iteration here is cold core. Remember, extratropical means cold core. So the middle of it is colder. See the little isotherms there? This would be an Arctic outbreak. It's a low pressure system aloft, but at the ground, it's a huge high. So here comes this cold front through North Dakota. Temperatures 30 below 0. It's January. And the pressure is like an altimeter setting of 3080 or 3090. But if you go aloft, it's a big low. That's how you know. It is a cold core extratropical low pressure system. Finally, the fourth and final iteration of all of these is a low pressure system over a low pressure system. So you go up to the Aleutian Islands, you do an analysis, and it's a big low. The pressure is like 28.75 or something, some really low altimeter setting. You go aloft, and it's a low pressure system there too. This would be your semi-permanent low. So once again, and in conclusion, we have got all of these things that we're looking at here. Let's do it here, okay. There. Warm core, tropical, and in all cases of tropical air masses, it's always high pressure aloft. High pressure aloft, high pressure aloft. With extratropical atmospheres, it is always low pressure aloft and cold core. And there you go. Any questions about any of that? A lot. Okay. Now we're going to talk about weather. And there are so many different kinds of weather, 100 different types of weather. I think we've talked about that. We're going to go through each one now and try to use this as an opportunity to understand a few other little intricacies about these meteors. So weather type number 00 is simply sky clear. There's nothing going on. If the cloud cover has not changed at all, then that is weather type number 2. If the clouds are retreating or dissolving, that's weather type number 1. If they are increasing, that's weather type number 03. Lithometeors. Now, I think we talked about this before, that there are hydrometeors, lithometeors, electrometeors, and photometeors. And so here now we're going to be talking about the first Lithometeor, smoke. That is weather type number 4. And you'll notice that there is a little letter here. That goes with the old airways description of weather. In METAR, it's FU for fumar. That if you see in a METAR observation, visibility, 6 miles in FU, that means smoke. But it also used to be K. K because S was for snow. Anyway, so smoke is basically just the result of combustion. Here it is coming out of towers, smokestacks. And so if something is burned and then there's aerosol that's left behind, that's called smoke. Also, there's a fire ash, which is an interesting type of, it looks like snow actually. So when forest fires are burning and some of the smoke, well, it's more than just smoke, it's like really, really big particles. And maybe you've seen this before. They will fall like snow. Next, we have haze, which is a lithometeor here, HZ. And the haze is simply a little bit farther down the line of smoke. Smoke that travels, I don't know, 75, 100 miles will eventually disintegrate into haze. And haze is just nothing more than airborne solids, aerosols. And generally particulate matter, generally 2.5 microns. That means that these are little bits of solid material that are 2.5 microns in diameter. That is your standard known as PM 2.5. It's a kind of pollution, and it is an obstruction division. It will lower the visibility. Next up is dust, another lithometeor. And this is simply particles of dust on the ground that is lifted up and then deposited someplace else. Now, weather type number 6 is simply dust that has traveled from someplace else and has arrived at your doorstep. Next up is volcanic ash, which is basically granite. This is something you really want to stay away from. It's something that, of course, can be an obstruction of vision, but it is also a significant hazard if you fly through, say, a volcanic ash cloud. Don't want to do that because that'll be very caustic to the engines, the structure, the window, everything. It'll just cause a lot of trouble. I remember once hiking up in the Cascades, where there are a lot of volcanoes up there, and then getting some dust on my glasses, and then I just try to clean my glasses, and bingo, they're scratched for life because it was actually volcanic dust that I was cleaning off of my glasses. Don't make that mistake. So here you can see volcanic ash, and there's some modest clouds from Mount St. Helens. That was a big explosion there back in 1980 in southwestern Washington State. And that's what it looks like. Stay away from volcanic ash if you possibly can. There are SIGMETs that are issued just for volcanic ash. Next up is blowing dust. Now, blowing dust is different from dust because it's happening right where you're at. So the dust is on the ground at your feet and it is being raised by the wind. That is blowing dust. Dust devils are interesting little features. We have a lot of those here in the summertime in Central California. This is different from tornadoes, even though they are vertical and they can be a pretty strong wind that can actually do damage. Dust devils can actually do damage well, not significant damage, maybe EF 0 damage. I remember decades ago, there was a carport in the Bakersfield area here that was destroyed by a dust devil. So a dust devil is caused by what's known as an autoconvective convective lapse rate, which is greater than 10 degrees Celsius per 1,000 feet. That means that the air is cooling off at more than 10 Celsius degrees, which is 18 degrees Fahrenheit per 1,000 feet, which is a lot. Usually it's because the ground is really hot, and that will cause the air to just automatically rise. You don't have to do anything. It just rises by itself because it is so less dense than everything around it. But then it will actually form these little these neat little tubes and things. And you've seen dust devils before, I'm sure. They're pretty cool. Anyway, that is weather type number 8. And it is METAR code number PO. And then dust storm in the vicinity means that it's not where you are, but it's pretty close. That's the dust storm is very specific. It is visibility less than a kilometer due to the dust. Then we get into the next group. This is minor fog. And weather type number 10 is BR. That's the broom, which you see on the METAR observations. Visibility 5/8 of a mile to 6 miles. So anywhere in there, this is 5/8, that would be considered BR. Once the visibility is less than 5/8 of a mile, which is also 1 kilometer, by the way, then we call the same thing FG fog. Ground fog is simply fog that is less than 6 feet high, and then right above it you can see well. That's ground fog. A widespread ground fog, the visibility might be reduced to less than 7 miles.
A question?
Yes, go ahead.
Why aren't the symbols like with the specific with the specific weather? Like you have the number for them, but like why is the symbol like when you show the PowerPoint? Oh, okay. I guess I'll just pull up the chart, but I was just saying maybe for like.
Those are the symbols. Those are the symbols that you were referring to?
Yes. And so then when you pull them up on the slide, right?
Uh-huh.
We don't see that symbol for.
No, because you saw it there. And I'm just simply describing what the phenomenon is. That's all. But here are all of the symbols, all 100 of them. And
right.
We can go into the who came up with these symbols and what do they mean, which is interesting too, I think. So anyway, yeah, for fog, it's basically just horizontal lines. That's BR, that is the baby rain or mist or whatever you call it. But serious fog is like number 45 down here. Now you got 3 lines. Now we're talking. But it gets more complicated than that because we're talking about, is the sky obscured or not? And so there are rules to that. And here you can see ground fog. Sorry about all the coughing. I just can't help it. Anyway, so we've got ground fog and patchy ground fog and things like that. So next up, speaking of symbols, we're going to go to this. There it is. Now that is the symbol for lightning. And lightning is, of course, you know what lightning is. We talked about it before. There's lightning. Lightning can be seen, but no thunder, okay? I mean, if it's a long way off, you'll get lightning. Lightning is caused by the electrical polarization of the atmosphere, where the top of the atmosphere up at the top of a cloud is positively charged. The base of the cloud is negatively charged. Here's the ground right here, and it is positively charged. Usually it's negatively charged, but in this case it's positively charged because it's a shadow under the base of the thunderstorm cloud, and we get this bolt of lightning right there, which can't remember if I discussed it or not, but anyway, the flow of electrons goes from the ground into the cloud, goes up, it doesn't come down. And in fact, you can kind of see it here. You can see like little tributaries that are actually going up into the cloud. And the rapid expansion of the air right around the flow of electrons, the bright 50,000 degree heat causes the atmosphere to expand so rapidly that it's faster than the speed of sound. So thunder, when you finally do hear thunder, is a sonic boom. All right, so we have that little lightning. Virga is this symbol right here. looks like a little happy face or something. That means that precipitation evaporates before it hits the ground. Then we have distant virga, number 15, and then precipitation in the vicinity, which is number 16 right there. Then, let's see, here's precipitation. This is virga not reaching the ground. This is precipitation reaching the ground. Then we have special convective activity. All right, weather type number 17 is known as a thunderstorm. So it starts off with lightning, there's that, but then we kind of make an R out of it by putting that little 90-degree square right there. So this is the symbol for a thunderstorm. Now that doesn't mean that it's raining, that just simply means you've heard thunder. When does a thunderstorm begin? It begins when you hear thunder. It's no more complicated than that. You don't have to have, special warm air comes here and there's an occluded front and this happens. And no, it's when you hear thunder. When does a thunderstorm end? A thunderstorm ends 15 minutes after the last thunder. So you give each clap of thunder a 15-minute period to exist. And that is how long a thunderstorm lasts. Now, normally you'll have thunder from this bolt of lightning. Of course, again, thunder is a sonic boom, and there may be more than one of those bolts of lightning. It's always caused by ice in the upper part of the atmosphere. Without ice in the top of the atmosphere, and by the way, the ice is the ice plates which brush against each other and strip off electrons. Without ice, you're not going to have any lightning, and without any lightning, you're not going to have any thunder. There is some cloud-to-cloud lightning. Yeah, lightning, by the way. So in a observation, it will be lightning in cloud, cloud to cloud, cloud to ground. Those are 3 different types. You can also have cloud to air or cloud to water. You can have all sorts of different types of lightning. And lightning will either be occasional, frequent, FQT, or continuous. And there are objective descriptions of that. Occasional would be like a flash every minute or so. Frequent would be less than every minute. And continuous would be like every couple of seconds. We talked about a squall line before, and here is a weather type number 18. It is a squall. Once again, a squall is, here's 10, 20, 30. So the wind is like this. You have some gusts here, but then it comes up here, stays there for a while, and then comes down. That is a squall. It's usually an outflow from a thunderstorm. Then we get to a weather type number 19, which is called a tornado. Who would have guessed? Number 19, of all things, that's the tornado. So this is a special convective type of activity. A tornado is caused by, let me just show you here. So here we have a thunderstorm, okay? In the middle of every thunderstorm is a tube. This is the main updraft in a big thunderstorm. Across the top of the tube comes a jet stream, a very strong wind, could be 100 knots, blows across the top of the tube, and then the tube is then stretched out because the wind is stretching out the top of this tube, which is the updraft. And when the top stretches out, that causes the bottom to stretch out too, to conserve the volume in the tube. And this tube that comes from the bottom of the cloud turns out to be the tornado. And all wind is blowing up into the cloud. So whenever you see a tornado or a funnel cloud or something like that, you should think that there must be a pretty strong wind blowing across the top of the thunderstorm. So that is a tornado. A tornado is a violently rotating column of air. It doesn't have to be the condensation funnel. And by that, I mean the cloud. You see the cloud right there. Sometimes it only goes to about there, but you can see the debris which is coming up. It's the column of air that is the tornado. And if it reaches the ground, then you've got a tornado. You could also, and that is an F, that is a plus FC, FC for funnel cloud. If it doesn't reach the ground, then it is called a funnel cloud. A funnel cloud is not really dangerous to people on the ground necessarily. It's something that is photogenic, perhaps, but that's about it. And finally, there's a thing called a water spout, which is basically just a tornado over water. And that too is a plus FC. A water spout will suck up fish and boats or anything else that's there, and can also deposit them many miles away. So, of course, remember, a tornado or a water spout is just a big vacuum cleaner. Everything is going up into the cloud. Recent weather. Okay, so now we're going to talk about things that are not happening now, but they did within the past hour, and there's a little bracket around it. So we will talk about the different kinds of weather a little bit later, but all of the 20s are recent drizzle, recent rain, recent snow, etc., recent hail, recent freezing precipitation. And here's a recent thunderstorm. That is weather type number 29. So if you just had a thunderstorm 45 minutes ago, but not now, that your present weather is weather type number 29. Now we're going to talk about blowing lithometeors. Blowing lithometeors. So you know what a lithometeor is? It's something that's not made out of water. It is dry, like haze or dust or sand or something like that. So if it is blowing and it is reducing the visibility, it is a obstruction of vision, then it is a blowing lithometeor. So here we've got blowing dust. All of the 30s are some sort of blowing phenomena, blowing dust. So there are all these specifics. So if the visibility is 1 to 6 miles and improving, that's weather type number 30. If you've got blowing sand, which is BLSA, it used to be BN because BS was blowing snow, then that is weather type number 30 as well. So here you can see blowing. The visibility is not all that bad, and it's getting better. So blowing sand or blowing dust. Of course, blowing sand is simply a bigger particle. You know, you can get sand blasted by strong winds in a desert where you've got or along the coast. You can go to go to Pismo Beach or something, and it's very windy, and you can get sand blasted by that too. You don't get sand blasted by dust, but you can get sand blasted to the point where it'll take paint off the side of a car. if the particulate matter or the grains are big enough. So here's a whole list of those, and these are all very specific situations where the visibility is 1 to 6 miles or less than 1 mile. It's improving, it's not changing. So that's weather types number 30 through 35. Blowing lithometeors. Now we have blowing and drifting hydrometeors, and you remember what that is? That's made with water. And of course, what sort of hydrometeors might there be? Well, drifting snow is one. And snow can drift into these big mounds that can be a big problem, by the way. They can cover things up. Drifting snow less than 6 feet is one thing. That's a weather type number 36, drifting snow, or 37, which is higher than 6 feet. And there are things called snow fences that are put out here. There are these fences. There they are. And they will cause this downstream effect where the snow will pile up in certain areas and not in other areas. And wherever the road is, you don't want any snow piling up there. So that's what the snow fences are all about. Then we have blowing spray, BLPY or BY. And that is simply bits and pieces of liquid water that are ripped off of the lake shore during a hurricane or something like that, and will reduce the visibility. Blowing spray, especially in hurricanes, is a big deal. Then we have blowing snow. In fact, here you can see a snow fence right over there on the side. Blowing snow, and here is the symbol for that right there, is simply snow that is raised from the ground. It's sort of like blowing dust, except it's snow, and it will reduce visibility. There is a pretty significant blowing snow situation. You can see the snow fence right there, which is placed there for a reason, right around roads and railroads and things like that. So 38BS or 38BLSN is blowing snow, and with the visibility less than a mile, that would be a pretty significant blowing snow. A lot of BS is what that is. All right, next up is the fogs, and that is 40. So everything in the 40 category is some sort of fog. Fog, of course, is liquid water droplets, basically a cloud that is on the ground. You can have patchy fog, that is weather type number 40. I guess 40 is actually fog in the vicinity, not where you're at. And if it's patchy, you get these little dense patches. That's weather type number 41. That is BCFG on a METAR observation. So here are all of the different iterations of fog. The sky can either be obscured or not obscured. If the sky is not obscured, so you have fog over here, but you can see clouds up here, then the sky would be partially obscured. In this case, the sky might be, say, I don't know, 4/8 obscured. But if the fog is so, and then you could see some clouds up there, you could see part of the sky, but not off on the edges. But if the entire sky is just obscured with dense fog, then that's called sky obscured. In which case the ceiling height would not be broken or overcast. It would be VV for vertical visibility, which we get into in a later class. So anyway, if the sky is obscured, that would be weather type number 43 fog if it is improving. Your classic no change is 45 fog. That means this one right here. It means that the sky is obscured. You can't see it's anything. It's just all fog all the time. Next, we get into freezing fog, and that is fog which is liquid, but it's in a below freezing environment, and so it is beginning to freeze on things. ZF is what it used to be, but FZFG is what it is now. This is fog depositing rime ice. And if the visibility is less than 7 but not obscured, then that's 48 fog. And you can see what it does there. It collects on the trees. Yes, okay. And then if the visibility is particularly low, then that would be even worse. Then we have a thing called ice fog, which is not really freezing fog, even though it has this little symbol. Ice fog is fog that is made out of ice. It does not deposit rime icing. The problem with the METAR observation is that you can, whenever the temperature is below freezing, they call it FZFG. But if the temperature is like minus 40 or something like that, you'll never have freezing fog. In that case, it's ice fog, and ice fog is what should be observed. That's weather type number 49. All right, and so that's halfway through all the weather types. Now we're going to go into the second half of them all, in which case precipitation is falling at the time of observation. So we're going to begin with, you can see a ball there. We're going to begin with drizzle. So drizzle is DZ. It used to be L because D was dust. And drizzle is simply precipitation with droplets that are less than 0.2 inches in diameter. Okay, it's just basically really small droplets. Light is 50, and then 51 is also light. So now we're going to talk about character of precipitation. Character of precipitation. This is its own thing now, precipitation. So there are three different characters of precipitation. One is continuous. Continuous precipitation means that it does not change its intensity. If it's light, it pretty much stays light. If it's moderate, it stays moderate. The second character is intermittent. Intermittent precipitation means that the intensity of precipitation does change, but changes very, very slowly. It goes from light to moderate to light to maybe stops, and then it starts again. The third and final character of precipitation is showers. So there you go. We've got continuous, we've got intermittent, and showers. Showers are precipitation that start and stop very quickly. They are caused only by cumulus clouds. Cumulus clouds, these are vertical building clouds. And so all of the precipitation from cumulus clouds are in a very narrow vertical column. It's not widespread. It's just right under that one little cloud. That's where it is. And so when that cloud gets to you, the precipitation starts rather quickly. And then when it goes by, it's over very quickly. So showers come only from cumulus clouds. Those are the three characters of precipitation: continuous, intermittent, and showers. Now, as far as the intensity of drizzle, we're talking drizzle right now. Light drizzle is known as, it's interesting because it doesn't take the rate of fall, it takes the visibility. So if the visibility is greater than or equal to 5/8 of a statute mile, then it's considered light, period. Moderate drizzle, which is a DZ with no plus or minus, is a visibility of about a half mile, half statute mile. And then heavy or thick drizzle is visibility of about a quarter mile. And that is how the intensity of drizzle is determined. So there's moderate drizzle, that would be about a half mile visibility. And then the numbers 52 and 53 are determined by whether or not it's intermittent or continuous. So you can have intermittent, which you will remember is a character of precipitation. It starts and stops very slowly. Continuous precipitation, that character means that it just doesn't change intensity. So all of the even numbers are intermittent. 50, 52, 54 are all intermittent. All of the odd numbers, 51, 53, and 55 are continuous. Here's heavy drizzle or thick drizzle. Next up, somebody needs to mute, I think, their microphone. All right, next up is a freezing drizzle. And this is, here is the symbol for that, as you can see. Freezing drizzle, here's drizzle, and then this is the symbol for going from liquid to solid. This is a lot like fog that is depositing rime ice. It starts off liquid, but it's a below freezing environment. So the drizzle, which is liquid, will then immediately freeze like this. That's a very dangerous thing. So FZDZ is freezing, drizzle. You can either be light or you can have moderate or thick freezing drizzle. Then we get into weather types 58 and 59. This is rain and drizzle mixed. It can be either light, that would be 58, or it could be moderate or heavy rain and drizzle mixed. That is weather type number 59. Then your standard rain. Okay, so standard rain is bigger than drizzle. It is rain droplets of water that are greater than or equal to 0.2 inches in diameter across. And that makes it rain. Then we also have intermittent, which is all of the even numbers here. This is the way they look. They're kind of vertically stacked. Or continuous, which is like this. And that would be precipitation that doesn't change its intensity. So there's light rain, intermittent or continuous. There's the rain. You can see rain falling. Moderate precipitation, and then heavy. Okay, so now how do we determine the intensities of rain? Well, this is different. So light rain is rainfall that is falling at the rate of 1/10 of an inch per hour or less. And this is the rate. So that means you don't have to wait an entire hour to determine what the rate is. If it is moderate rain, which is not doesn't have a minus or a plus, that would be 0.10 to 0.30 inches per hour. And that makes it moderate. If it is heavy rain, which is the plus, that is greater than 0.30 inches per hour, the rainfall rate. And that's it. So rain, the intensity of rain is determined by the rainfall rate, but the intensity of drizzle is not. The intensity of drizzle is determined strictly by visibility. If the visibility is 5/8 of a mile or higher, it's light. If it's a half mile, it's moderate. If it's a quarter mile or less, it is thick or heavy drizzle. Now, freezing rain is probably the worst type of weather that can exist because it is really, really dangerous. These are regular raindrops that are made out of liquid, but then they immediately freeze as soon as they hit the ground. And they will then freeze on infrastructure. They will freeze on power lines. They will freeze on driveways and runways. And they will cause all sorts of trouble. They will freeze on trees. So light, moderate, and heavy freezing rain is based upon the rainfall rate, just like rain was. Here you can see the damage that can be done by freezing rain. It simply will cause ice to accumulate on things, get very heavy, and just gravity pulls them down and destroys them. So freezing rain is in many ways worse than snow. Liquid and frozen precipitation together, those are the late 60s, so 68 and 69 will either be light rain and snow or light drizzle and snow. And then the moderate and heavy version of that would be weather type number 69. Now we get into frozen precipitation. There are many different varieties of that. Of course, snow is first that comes to mind. And of course, as with drizzle and rain, we have intermittent and continuous versions of that. So light snow, and here you can see snow accumulating, light and moderate and heavy snow would accumulate. Here's light snow. Now, if you remember the rules for intensity of drizzle, it's the same for snow, which again is not, it's counterintuitive to me at least. So when it comes to light snow is visibility greater than or equal to 5/8 of a statute mile. Moderate snow has nothing to do with how much snow is falling. It's crazy. It's the visibility of about a half mile. And heavy snow is called heavy if the visibility is about a quarter mile or less. It's the same thing as with drizzle. Here's moderate snow that can be intermittent or continuous. And here is heavy snow. 75 snow, continuous heavy snow with low visibility. So here are the symbols. This is light, moderate, and heavy continuous snow. This is intermittent, intermittent, and intermittent, light, moderate, and heavy snow. Next, we got to weather type number 76, ice crystals. Ice crystals are similar to ice fog. This is precipitation, the only precipitation that can fall from a clear sky. So there might be no clouds at all, yet it's precipitating. How does that happen? The temperature is usually less than minus 22 degrees Fahrenheit. So it's extremely cold. It only happens in the winter. And you get these neat little effects. So here's the sun, and this is called a sundog. This is also a 22-degree halo. And you will find 22 degrees away from the sun, that is where the ice plates will be causing these little pillars of light. They can be beautiful. I spent a number of years in Alaska, and when it was very, very cold, at night, I was a forecaster at Elmendorf Air Force Base, and of course, the aerodrome, the airport has lights, red lights, and blue lights, and green and white lights. And above all of those lights were these vertical pillars, and it looked like a little fairyland. It was really quite pretty. Those are ice crystals. Then we have snow grains, which is basically frozen drizzle. SG is the METAR code for that. You can see some. Normally, you'll find snow grains falling in very stable air masses. Next up, we have weather type number 78, which is snow pellets. And these come from cumulus clouds usually. They can be sort of hollow on the inside. It's an interesting type of precipitation. Next up is weather type number 79, sleet. And sleet you've probably all heard of. Sleet is very complicated because here you have the ground down here, and then you have precipitation here. And so it is below freezing, like it is minus 2 degrees, and then it has to be like plus 2 degrees here, so it's warmer, and then it has to be colder again down here, so you have this like layer cake of temperature, and that causes the snow to melt and then to freeze again, and you get little ice balls. These are not hail. This is an extratropical low pressure system. This is fairly stable air mass. This does not come from cumulus clouds. This is just sleet, which used to be E because S was snow. Ice pellets. It's also known as ice pellets. Then we get into the showers, and the symbol for showers is this. And here you can see it down here. And it sort of indicates that the precipitation is falling at a spot right down there, because showers, which is one of the 3 characters of precipitation, falls only from cumulus clouds. It's all vertical, 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 and so all of the precipitation is just in this little spot down here. So it's a character of precipitation. So RW is what it was. W was the term for showers. SHRA is a light rain shower. The actual intensity is again based upon the less than 1/10 is light, 1/10 to 1/3 is moderate, and anything more than 0.3 is considered heavy rain showers. And they fall, they start and stop quickly. Weather type number 81 is a moderate or heavy rain shower. Now there is another version here, and this is a violent rain shower, and that would be rain falling at greater than or equal to 1/2 inch per hour. That is a little bit different. That's like plus. And that would be weather type number 82. 82. If rain and snow is mixed in showers, then we call it weather type number 83. That's if it's light. If it's moderate or heavy, then we call it weather type number 84. Weather type number 85 is a light snow shower, and snow showers are just like any other, except they're snow, not rain, and they do come from cumulus clouds. You'll see snow showers in lake effect snows quite often. So here is a light snow shower, weather type number 85. If it is moderate or heavy, and of course, again, remember that the intensity of snow is based on visibility. Visibility only. So weather type number 86 is moderate or heavy snow showers. Now we're going to get into hail, and we're coming to the end of all of this, as you can probably tell. So hail, all hail comes from some sort of cumulus cloud. So hail is caused by updrafts, and here is the 0 degree isotherm right there, that's the freezing line. And so what happens is that rain will develop and freeze into a little ball and then fall back down below the freezing level, and then we'll go back up by another updraft and will finally fall to the ground. That's how hail develops. Now, small hail is weather type number 87. That is hail showers that are less than a ½ inch in diameter. And there they are. And you can have hail showers without any thunderstorms. Happens a lot in the winter time in places like Washington, Oregon, and Southwest Canada. A moderate or heavy small hail, that would be also known as GS on METAR, would be weather type number 88. There it is. Looks a little bit like snow pellets there. And then number 89 is a larger hail. This would be hail that is greater than a ½ inch across, up to maybe 3/4 of an inch. So a light hail shower would be weather type number 89. And this is GR, not GS. Again, GS is a ½ inch, and then maybe down to pea size. We get that in the Bakersfield area sometime. And then bigger hail, but not severe, is a GR, that is a ½ inch or greater than ½ inch, I should say. Moderate or heavy hail shower would be weather type number 90. And then finally, we're going to get into precipitation following a recent thunderstorm. If you remember, a recent thunderstorm is weather type number 29, but it can still be raining. And if it is, that's weather type number 91. Light rain after a recent thunderstorm. If it is a moderate or heavy rain after a recent thunderstorm, that is weather type number 92. Weather type number 93 is light snow following a recent thunderstorm. And moderate or heavy snow following a recent thunderstorm, and that does happen, is weather type number 94. And finally, last but not least, is the full-blown thunderstorm. So if you remember, if it's just lightning, it's that. If it is thunder but no rain, it's the thunderstorm number 17. But if there is rain, then it is TSRA. That's a thunderstorm. You hear thunder with rain. And that is weather type number 95. Your classic thunderstorm is weather type number 95. If there's snow with it, then it's TSSN, and that's also weather type number 95. Now, if we've got some hail, which is greater than a ½ inch, but less than an inch, that is weather type number 96, and you can have rain or snow with that. Now we have a T+, which is a severe thunderstorm. The criteria for a severe thunderstorm is, one of them is wind gusts of 50 knots or more, which is 58 miles per hour. If you have a squall line that goes through, then you would have a severe thunderstorm. That would be weather type number 97 with strong wind gusts. You can have snow with that as well, and that's also weather type number 97. Weather type number 98 has visibility less than 7 miles due to rain and blowing dust. And there it is, TSBLDU. And finally, the Coufferet at the very end, it's weather type number 99. That is a severe thunderstorm with large hail. What is large hail? 1 inch in diameter or greater. It used to be 3/4 of an inch, but that then changed in 2007. So weather type number 99, a severe thunderstorm. It used to be T plus, now it's just TSRAGR. And there it is, large hail and thunderstorm. And there you go. We have gone through all 100 different types of weather. I can't believe it. We did it. And we had a long discussion before this too. So this was a pretty good class. Here's aviationweather.gov. That's the place to go to get all the information about METAR observations. And we've done it, everybody. We've done it. This was synoptic weather, everything that you ever want to know about different types of weather, characters of precipitation, squalls. What is thunder? It's actually a sonic boom. How is lightning made? It is the polarization, electrical polarity. Lightning generally flows from the ground up. How do you determine the intensity of precipitation? It is less than 1/10 of an inch, then 1/10 to 1/3 of an inch for moderate, for rain, and then greater than 1/3 of an inch after that. There's intermittent, there's continuous, and showery. Those are the characters of precipitation. So we learned a lot. Here's the assignment. Watch extratropical cyclones video and weather and aviation, weather fronts and thermal wind. And then next time, by that I mean day after tomorrow, Wednesday, we're going to look at part D. We're going to talk about forensic aviation weather. And this specifically talks about weather-related aircraft accidents and what you need to know about that. Okay, are there any questions about anything from today's class? We got a few people that are still on here. And
I have a question about like with an
yes.
AWOS, say there's like jets operating in the area and they are flying over the speed of sound, would that AWOS pick up the sonic booms and register it as thunder?
Oh, no, I don't think so. You're talking about an AWOS observation that hears a sonic boom and thinks it's thunder?
Yes.
No, that won't happen because when a thunderstorm is shown on an AWOS or an ASOS observation, there has to be lightning nearby, and we have a whole lightning grid. So we know using GOES satellites and a few other things whether or not there's lightning. If there's no lightning, there will not ever be thunder mentioned. Now, a human being, at LAX or something like that, they may hear a sonic boom, but they will know better that it is not thunder. That's a good question, Chris. Thanks for asking. Any others? Okay. All right. If there are no other questions, then we will bring this to an end. I'll hopefully see everybody on Wednesday when we talk about forensic aviation weather. It'll be an exciting class. Thanks so much, everybody, and have a great Monday.
You as well. Bye.